position will not be changed. Okay. So now in the insertion process, okay, actually we need to perform a embedded search operation. Okay. So the first thing to do is that, okay, determine whether or not the element that we want to insert is already contained in the binary search tree. Okay. Now in the basic definitions, we do not allow duplicate values or duplicate key values in the binary search tree. So if the data object that we are trying to insert is already there, okay, we don't modify the tree. Okay. And the design of the function will return a pointer that points to the node, okay, that has been created, or an existing node that is storing the key value. Okay, so that's why here we, in the design of the function, we return the pointer p. Okay. Now if we don't find the value in the tree, okay, then we need to know the place at which we fall out of the tree. Okay, so when the pointer p eventually, okay, equals to node, we need to know, okay, where it has fallen out of the tree. So we need to make use of another pointer variables. So when we are doing the traversal, okay, so we keep the pointer q to point to the parent of p. Okay, so when p fall off the tree, we still, okay, know the point of insertion, okay, which is represented by the pointer variable q. Okay. So after that, then we create the new node. Okay, we create a new node. We store the value, initialize its left and right pointer to the node pointer. Then we make one more comparison with q. Now if q is the node value, then it means that the original binary search tree is empty. Okay, then after the insertion, the root node of the tree will be replaced by v. Okay, now since there's a chance that we will modify the value of root, then the parameter root should be passed to the function by reference. Okay, so remember this. Every time it's within a function, that, okay, parameter may be modified, and you want that change to be observable when the function returns. After the function returns, then that parameters must be passed by reference. Now if q is not the node pointer, then we compare x with its data. If x is less than the data at q, then the new node will become the left child of q. Otherwise, it will become the right child. And after the insertion, according to the requirement of the insert function, we returned the pointer v. Now, the delete operation will be more complex than the insert operation. Now, to delete a node from a binary search tree, okay, we need to preserve the properties of the tree. Okay, meaning that all the data values on the left-hand side of a root must be less than the value of the root, and all the values on the right subtree must be greater than the value of the root. Okay, so when we consider the delete operation, there are three separate cases, okay, to consider. Now, the first case is that if you are going to delete a value x, and it happens to be a leaf node in the tree, then this will be the simplest case. Okay, now here in the diagrams, the left-hand side is the original structure of the tree, and the right-hand side shows you the revised structure after the deletion. Now, if we are going to delete the value 15 from the tree, okay, now if this is located in a leaf node, then we simply remove it from the tree. We don't need to do anything with the other nodes in the tree. Okay? So to support this operation, once again, when you traverse the tree, you need to keep two pointer variables. Okay, the pointer variable that points to the node that contains the value x, and the other pointer variable will point to his parent. Okay, otherwise you will not be able to modify the pointer, the left or right pointers, okay, of the parent of the deleted node. Now the first case is the simplest. If the value that you want to delete is located in a leaf node. Okay. Now the other case is that if you want to delete a value and it is located in an internal node, and that internal node has one empty subtree and one non-empty subtree. Okay. So if this is the case, okay, then you will remove that node and connect the non-empty subtree to his original parent through the corresponding pointer. Okay, now in this case, if you are deleting node number 5, then after the deletion, okay, the root of the subtree, the root of the non-empty subtree is 6. Then 6 will become the right child of node 3. So this will be the updated tree structure. Now removing an internal node with one empty subtree, then you will see that this part of the tree, it behaves as a linked list. Okay, because it's degenerate to a linear structure. Okay, then the deletion is like the deletion of a node in a linked list. Now the third case is that, okay, you want to delete a value, and that value is located in an internal node with two non-empty subtrees. Okay, now if you have two non-empty subtrees, how to modify the tree with the minimum changes such that we can preserve the properties required by a binary search tree? Now the way to do it is that if you need to remove an internal node with two non-empty subtrees, first of all, we will identify the in-order successor of the node that you want to remove. Okay, now what is the in-order successor? The in-order successor is the value that follows the deleted data in the in-order traversal. Okay, so if in the in-order traversal, after 11, the next one is 12. So 12 is the in-order successor of 11. Now where is that in-order successor? The in-order successor is always located in the right subtree, or put it the other way around, is that it is always located as the leftmost descendant in the right subtree of the deleted node. Okay, so you go to the right subtree and move along the left pointers until you cannot move further. That node will be the in-order successor. Okay? Now the delete operation will have two steps. First of all, you will remove the in-order successor. Okay, now it is guaranteed that the in-order successor will have an empty left subtree, because since you cannot move further down through the left pointer. Okay, then the left pointer of that in-order successor must be a null value. Okay? Then, first of all, you remove the in-order successor by connecting his right child to the left pointer of his parent. Okay, now you have now 13 becomes the left child of 14. And then you will replace the node that you want to delete by his in-order successor. Okay, so you will move his in-order successor to replace the deleted node. Now the other option, okay, is to replace the deleted node by his in-order predecessor. Okay, so either options are acceptable. Okay, however, when we write programs, okay, we will design the program codes to either, okay, do the replacement using the in-order successor or in-order predecessor. We won't write the programs in such a way that, okay, we roll the dice and then based on the outcome we go to use the in-order predecessor or use the in-order successor. It duplicate the effort in writing the programs. Okay, so we will stick to either one option. Now, here is one example. Okay, suppose this is the original structure of a binary search tree, and we performed a sequence of insert and delete operations to the binary search tree. And we want to find out what will be the structure of the tree after each of the update operation. So, when we are inserting the value 73 to the search tree, okay, where will we put the value 73? We start from the root. 73 is greater than 65, so we move to the right hand side. 73 is less than 77, so we move to the left hand side. Now 73 is greater than 67, so 73 will be placed at the right child of 67, so 73 will be added here. Okay. Now the next insertion is to insert the value 35. We start from the root. 35 is less than 65, we go to the left hand side. Then 35 is greater than 28, we go to the right hand side. Then 35 is greater than 33, we go to the right hand side. And then 35 is less than 40, so 35 will be placed here. Okay, so 35 will be placed here. Very interesting to see is that this is a question in some previous exam, and more than half of the students will put 35 here. Okay, I don't know why is the reason, but the correct place to put 35 is here. Now, okay, based on this tree, the next thing we do is to delete the value 33. Now, deleting the value 33. Now, 33 has one empty subtree and one non-empty subtree. Okay, so after the deletion, the root of the non-empty subtree will be connected to the parent of the deleted node. Okay, so after the deletion of 33, 40 will become the right child of 28, and 35 remains to be the left child of 40. Then the next operation is to delete the root 65. Okay. Now to delete the root, okay, we go to find his in-order successor. Now the in-order successor is in his right subtree, follow the left pointers. Okay, to find the leftmost descendant. Now 67 is the in-order successor of 65. And after deleting 65, his in-order successor will be relocated. Okay, then 73 will become the left child of 77, and 67 is used to replace 65. Okay. Some years ago, I showed the students about the full program for the deletion, but the course is a bit long, lengthy. Okay, and as a result, it may not be that helpful. Yeah.
The last one, the E65, what is the predecessor for 65?
You can also replace it by his in-order predecessor, 40. Okay. Either answer will be acceptable, but if there are more deletion in the questions and some other internal nodes with two non-empty subtrees are to be deleted, then your answer must be consistent. You don't use the in-order predecessor in one case and the in-order successor in another case. Okay. Now, any questions on this part? Now, the basic binary search tree is simple. I haven't uploaded the notes, but some years ago actually it was included, but later on it was not included anymore. It's the discussions of a improved binary search tree. Now, what is the possible disadvantage of the binary search tree? The possible disadvantage is that the tree may not be balanced. Okay. Now, if the tree is not balanced, then when you perform the insertion, deletions, or searching, the time will be degraded. The performance will be degraded to order n. So you lost the advantage. Okay. So how can we make sure that the insertion, deletion, and the search operations is always order log n? One way to do it is that every time you modify the tree, you keep it in a form that is balanced. Now, weight balance is one possible way. Okay, when you have a tree that is weight balanced, then if you have n nodes, the height of the tree is always maximum, order log n. It cannot be degenerate to a linear structure. Otherwise, it's not balanced. Okay. Now, weight balance is one way to keep the tree balanced. The other way, or more commonly used approach, is to maintain the tree to be height balanced. And this tree is given a name called the AVL tree. It is named after the inventor. That with the name start with A and the other one start with V, so it's called the AV. Then the third office start with L, so it's the AVL tree. Now the idea of height balance tree. Now this part will not be in the exam. Don't worry. Now the idea of a height balance tree is that okay, every time we update the tree, we maintain it. The left subtree, the height of the left subtree and the height of the right subtree differ by no more than 1. Okay, and the definitions of the height of a tree in this application is that a tree with one node is considered to have a height of 1, not 0. Okay, so this is the definition used in this case. Okay. Now, the basic idea, okay, can be explained through some diagrams. Okay. Now, if this is the original, okay, binary search tree, okay, and the label represents the height. Now, if this subtree, the height is h, okay, and these two subtrees, the heights are also equal to h, then the overall height of the tree is h plus 2. Okay, then it means that the left subtree of the root A is taller than the right subtree. Okay, so in this case there's a +1 label in the root, meaning that the left subtree is taller than the right subtree by 1. Okay. Now if you perform one more insertion to the tree to the left hand side, now suppose the new node is put here. Okay, then the height of the left subtree of A will become 2 plus the height of the right subtree. Okay, now the differences between the height of the left subtree of A and the right subtree of A becomes +2. Okay, now the tree is not balanced. Okay, then after the insertion, the algorithm will do a rebalancing operation with constant time performance. Okay, if the rebalancing requires non-constant time, then okay, it will incur too much of overhead. Now the rebalancing will be called a so-called a rotation operation. So we rotate the subtrees. Okay, and in this case, when the newly inserted node is inserted to the left subtree of the left subtree of the imbalanced node, then we call it to perform a LL rotation, left and left. Okay. Now in doing the rotation, we will make node B to become the new root, and swap the right subtree of B to become the left subtree of A. So we do a rotation of the tree for this subtree structure. After the rotation, the overall height of the subtree remains equals to h plus 2, which is the original value before the insertion. So the overall tree will still be balanced. So the modification of the structure of the tree will be limited to one single rotation. Okay? So the other possibility is that the newly inserted node is in the right subtree of the closest ancestor that becomes imbalanced. Okay, then we perform a RR rotation. We rotate the other way around. Okay, and once again B becomes the new root, and the left subtree of B will become the right subtree of A. And after the rotation, the overall height of the subtrees remained the same. Okay. The other two types of rotation, okay, is that the inserted node is inserted to the right subtree of the left subtree of the imbalanced node. Okay, now it's the right subtree of the left subtree, so it's a LR rotation. Okay, now you can understand this. Okay, meaning of the label LR means that the insertion path is to the left and then right. Okay. Now in the LR rotation, okay, this will be the three nodes involved, A, B, and C. And C will be chosen to be the new root. Okay. And A, the value of A is greater than C, so A will be on the right hand side. Okay. And okay. Now if C becomes the new root, okay, B is on the left hand side. Okay. Then the two subtrees of C will be, the left subtree will be placed onto the left hand side, the right subtree will be placed onto the right hand side. So they will be redistributed. Okay, and this is a LR rotation. So you have a symmetric rotation, that is the RL rotation. Okay, it will be the same. So every time when you make an insertion to the tree, then followed by the insertion, there will be a rotation operations to make the tree balance again. The same for deletion. Okay, and actually, in the some languages, the built-in data structures like the tree set in the Java language, it is based on a balanced binary search tree. Okay, and there are different approaches to do the balancing. Okay, so the height balance tree is one of the first ideas. Okay, and the tree structure used in the Java library is the red-back tree. Okay, so this is some kind of idea that is doing the rebalancing. Okay, so by maintaining the tree in some balanced form, then it is guaranteed that all the insert, delete, and search operations can be done in log n time. Okay. Now, any questions about binary tree? If not, then we will introduce to you another concept. It's called the general tree. Now, binary tree has a restriction. Okay, a node can have only 2 children, at most 2 children, the left child and the right child. Okay. Now, in the real life, very often we have some hierarchical relationship amongst the data objects. Okay, that cannot be strictly modeled by the binary tree. Okay, so like a family tree. In family tree, a parent can have more than 2 children. Okay, in the past. Okay, and so here the definition of a general tree is similar to a binary tree, with one exception is the definition of the subtree. Okay. Now, in the definition of a general tree, if the tree is not empty, then there's one special designated node called the root node of the tree, and the remaining nodes are partitioned into m disjoint sets. Okay, m can be any value that is greater than or equals to 0. So there's no upper bound, okay, specified in the definition. Okay, so theoretically m is unbounded. Okay, there's no specific upper bound. And the other factors is that the trees, the subtrees, are not ordered. Now, in the case of binary tree, the left subtree and right subtree are implicitly ordered. Now, there's one tree called the left subtree, the other tree is the right subtree. Okay, but in a general tree, we can simply say that it has m subtrees and there's no predefined orders. Okay, that is imposed onto the subtrees. Okay, but in the design of a program, we may still, have some implicit ordering, okay, of the subtree, because when we are doing the traversal, the program will still visit one subtree before the other subtree. Okay, but according to the definition, okay, the subtrees are not specified to be ordered with respect to each other. Now here is one example of a general tree. Okay, now you see that for node C, it has a degree greater than 2. Okay. And when we draw the tree structure, when a node has only one child, we won't draw it to be inclined towards the left-hand side or the right-hand side as in the case of a binary tree, because in a binary tree, the child must be identified to be the left child or right child. Okay, but in the case of a general tree, if it has only one child, then you only have one link, and there's no particular, okay, so-called inclination in the drawing of the graph. Now, with this structure, okay, we can adopt the same definitions of some other relationship, like parent-child, ancestor-descendant, leaf node, internal nodes, length of the tree nodes, and the depth of the trees, and so on. Okay, those are similar to the case of a binary tree. Now, how are we going to represent, or meaning that we specified a general tree? Okay, now if we are specifying as a text format, then we will use the nested parenthesis representation. Okay, so in the nested parenthesis representation, okay, so we have a bracket. Okay, everything enclosed within the bracket represent a general tree, and the first label on the left-hand side after the open bracket is the root node. And then the subtrees are placed in brackets. Okay. Then you will see that this part is the first subtree of A. And then this part will be the second subtree of A. And here is the third subtree of A. Okay, now you can see the structure shown here. Now A is the root. Then the first subtree, did I make any mistakes? Okay, sorry, I made mistakes here. Okay, counting the bracket is not correct. This is the second subtree of A is the root is C. Now the first subtree of A contains 3 nodes enclosed in the next level of bracket. Okay, and the root of the subtree is B. Okay, and within B, it has 2 children, H and J. And then the second subtree of A, C is the root. Okay, then the first child of C is D, and D has no children. The second child is E. Okay, and where's D? D, E. Okay, and E has a child, G. And F is the first child of C. Now this is the usual representations for defining a general tree in a data file. Okay. Then how about the representations in a program? Now one way to represent a general tree or a tree that allows a higher degree structure is that in a knot structure, we have the data field and then a certain number of pointers. Okay, now if in your structure, in your knot structure, if you have up to k pointers, then your program will be able to represent a tree with maximum degree equals to k. And we call this a k-ray tree. Now, one major problem with this representation is that in an application, okay, if you are dealing with general tree, you don't know what will be the maximum degree of the data that you need to process. Okay, so if the degree of the data set happens to be greater than k, your program fails. Then what you do? You modify the value of k, and then we compile the program, run it again. But for the next data input, the next set of input data, you don't know. It failed again. Okay, so it's not a very good approach. The other disadvantage, okay, that is more important in the past, is that the memory utilization of the pointers in your knot structure can be relatively low, because when you have a tree with high degree, it is only a small percentage of nodes with a high degree. Most of the other nodes will have a small degree. Okay, then many of the lengths in your data structures are having the node value. Okay, so you are wasting the memory resources. Then what will be a better approach to represent a general tree in a computer program? The answer is that we represent a general tree by using a binary tree. So we use a binary tree to represent a general tree. The way to do it is that we give different meanings to the left and right pointer of the tree node. Okay. Now in a binary tree, the left and right pointer means that they are pointing to the left child and right child. Now when we use a binary tree to represent a general tree, we use the left pointers to represent the parent-child relation. Okay, so the parent will have a left pointer points to the first child through the left pointer. And then in the child, if it has some siblings or brothers, then they are connected through the right pointer. Okay. So for this general tree structure, A is the root. Now in the binary tree representation, we also have A is the root. Now B is the first child of A. Then B will be connected to A through the left pointer, which means the parent-child relation. And C is the second child of A, so C will be connected to B through the right pointer of B. Okay? Now, H is the first child of B, so H will be connected to B through the left pointer. And J is the second child of B, then J is connected to H through the right pointer. Now similarly, for D, E, and F, they are all children of C. So D is connected to C through the left pointer, and then E is connected to D through the right pointer, and F is connected to E through the right pointer. Okay, and G is a child of E, then G is connected to E through the left pointer. Now this will be the physical structure, but the logical meaning is the general tree. Okay, but the physical representation is a binary tree. Now what is the advantage? A knot can have arbitrary number of children. They are all connected through the right pointer, and this link can extend without a predefined upper bound. Okay? So there's no limit, preset limit on the degree of a knot. Okay. But the logical meanings, okay, of the two pointers will be different. Okay. Now, when we have a different meaning assigned to the variable, then when we decide the algorithms to manipulate the general tree that is represented as a binary tree, the programs will be different. Okay, so we need to make appropriate changes to the program statements. Now let's take a look at some examples. Now let's consider the case that we want to count the number of leaf nodes in the general tree, which is represented as a binary tree. Now, in the original general tree, there are 1, 2, 3, 4, 5 leaf nodes. Okay? But in the binary tree representation, H is not considered as a leaf node if it is a binary tree. Okay, it is considered to be an internal node if it is regarded as a binary tree. However, if it is a general tree, it is a leaf node. Then what is the requirement for a node to be a leaf node in the original general tree? Now, if the left pointers of the node is a node value, then it is a leaf node in the original general tree. It has no children. Okay, when there's no children, it's a leaf node. Okay, so the requirements is modified. Now, a leaf node in the binary tree that represents a general tree, the criteria is that if the left pointer is null, then it's a leaf node. Okay. Now the program to find out the number of leaf nodes in the general tree, once again we use recursion to solve the problem. Okay. Now we consider the base case. The base case is if the tree is empty, I have nothing to do. Okay, so if the tree is empty, now the pointer that you receive represents the pointer that points to the root of a subtree in the general tree. Okay, now if the subtree is empty, then there's nothing. Okay, then you return 0. Okay, now if the node has the left pointers equals to null, then it has no children. Okay, then it means that in that subtree you have one leaf itself. Okay, then you return 1. Now, if those two base cases are not true, then you will proceed to do the counting. Now, you are considering a root node of a general tree that have one or more subtrees. Okay, then the number of leaf nodes within this subtree will be equals to the sum of the leaf nodes in each of the subtree. You add it up, right? Okay. Now, a subtree, a node can have any number of subtrees. Okay, so that's why in the algorithm we need to use a while loop to visit or process the subtrees one by one. Okay. Now the pointer P will first follow the left pointers to reference the first child of the parent. Now P following the left pointer is now referring to the first child. Okay. Then the loop here says that as long as P is not null, then it means that for every subtree of the root, we find out how many leaf nodes are there in that subtree using recursion. Accumulate the returned value. Then we move on to the next subtree. Okay. Now moving on to the next subtree, we follow the right pointer. When we have processed the last child of the parent, then P will have the null value and the while loop stops. Okay, then we return the final results. Another example. To determine the height of a tree represented as a binary tree. Now in this example, we use a slightly different definitions. We say that the height of a tree with only the root is equals to 1 instead of 0. Okay. Now, to find out the height of the tree where the root is P, okay, the base case is if the tree is empty, then the height is 0. Okay. Now, if the tree is not empty, okay, then we will find out the maximum height of all the subtrees. Okay, so we will find out the height of individual subtrees one by one. Okay, then once again, we have a for loop. Okay, so P will first start from the left child of the parent, the first child in the general tree. Okay, and H is the largest height that we know up to this moment. Okay, and for every subtree root at P, okay, when P is not null, we find out its height using recursion. We save the returned value in the variable T and then compare with the largest height, okay, that we know up to now. If T is greater than H, replace H by T. Then we move on to the next subtree. Okay. After the loop terminates, okay, the overall height of the subtrees, the overall height of the tree will be 1 plus the maximum height of the subtree. So now here is the typical structures of the recursive algorithm that operate on a general tree, which is represented as a binary tree. Okay. Now we receive an input. Okay, the pointer that reference the root. The base case will be usually okay. One of them is that the input pointer is a null value, and is one of the base case. There may be another base case. It depends on the problem. Now, if it is not the base case, then you do some computation with the root if appropriate. Or you may need to do the computation with the root after the traversal of individual subtrees. It depends on the problem. Okay, meaning that either you can do a p-order traversal or do a post-order traversal of the general tree. Then you will use a loop to process each of the child of the root. Okay, then you start from the left pointer. Okay, then in this case you have a while loop. As long as P is not null, you do some computation with the subtrees using recursion. if you need to accumulate the results, whatever, okay, that is required according to the problem. Then you move on to the next subtree. Repeat the loop until you have processed all the subtrees, and then you return the final result. Any questions? If not, then let's take a break for a few minutes.